Okay, we're going to get started with chapter 5. So here's the difference, and I want you to know the big picture when we're covering all of these different chapters and the reason they're done in this order and why we're covering what we're covering. So in chapter 5, it's called Electrons in Atoms, right? So electrons in atoms means we're going to focus on just the electrons part. So back in chapter 4 and 25, we spent time looking at the entire atom, and we even looked specifically at the nucleus where the protons and neutrons are. But it turns out that for atoms, the most important part isn't the nucleus, because the nucleus is buried in the center of the atom and doesn't come in contact with anything else generally. Most of the time, it's the electrons that are on the outside that actually come in contact with other atoms. And that makes them really important. Right? And that's why we're going to cover electrons in atoms specifically in this chapter. Okay? And this is going to help us to explain a lot about why certain elements have the properties that they do, and eventually is going to really help us in determining how other atoms can join together chemically, right? They can chemically bond to each other. So in chapter 5, we've got 3 sections, right? Each section has a series of things that you should be able to do. So these are the objectives for this chapter. So by the time we get to the test on chapter 5, right, there should be a way for you to understand the different models of the atom. So we're going to go to different models of the atom. We're going to talk about electron configurations. That's going to be a big part of this chapter, right? Even though there's only one objective here, that's a big part of this chapter. And then we're also going to talk about what's the relationship between electrons and light waves, right? We're going to get into just at least some of that in this chapter. All right, so we're going to first start off with a little bit of a review back from chapter 4. Remember, in chapter 4, we were kind of coming up with this idea of what does the atom look like? And it was a series of experiments over the years that determined that. And the very first one that really helped us come up with an idea of what the atom looks like is the J.J. Thomson experiment, where he was working with that cathode ray tube and the magnets. And he was holding up magnets to the cathode ray tube, and the ray inside of it was bending. And that led to the conclusion that atoms must have these negative parts to them. And that's where the idea from the electrons came from. And so J.J. Thomson, at that time, he thought, okay, well, if an atom has negative parts, then it's also going to have a positive part. And so he imagined that an atom was this big ball of positive charge with these little negative electrons stuck to the outside of it. In fact, at the time, he called it the plum pudding model, right? Because in his day, a very fancy dessert that you would see at dinner parties would be plum pudding. Right? And plum pudding would be this pudding, and then would have whole plums stuck into the outside of it, sort of as almost like a decoration. And so he imagined that's sort of what an atom would look like. Now, that had to be changed. That idea of the model the atom had to be changed by Rutherford's experiment, right? He did the gold foil experiment. And he determined that that ball of positive charge was not big. It was actually really, really small. And that's where the idea for the nucleus came from. And so after Ernest Rutherford did his famous experiment, then our idea of what the inside of the atom looked like changed. And we thought it looked more like this. So we have this much smaller ball of positive charges, that would be the nucleus. And then the electrons are not stuck to anything. They are just floating around the outside. And in fact, you've seen this several times in your life, I'm sure, right? A lot of times people say, oh, that looks like the symbol from Jimmy Neutron, right? Or maybe if you've ever seen like the Big Bang Theory, that's like one of those symbols they show. It's really the symbol they show anytime something is meant to be science-y in any way, right? So if it's meant to do something with science, this is the symbol you generally see with it. And I always think that's ironic because that's wrong. That's not even the right symbol. That's it. The reason why, I guess it looks cool, but it is not what we believe the atom is really like here in this modern age. Okay, since Ernest Rutherford, we've learned a lot about the atom. One of the things that we have learned is, yeah, there's a tiny little nucleus in the middle, but the electrons don't just randomly fly around anywhere they want to. There are specific places. There are definite orbits. There was a scientist by the name of Niels Bohr, and after a series of experiments, his conclusion to all of that was that electrons are more like the planets going around the sun. They have definite orbits and places where they can be and places they can't be. And so there was this idea that there was a structure to the electrons in the atom. Now that was probably back in the early 20th century. And so in the 100 years since then, we have revised that even further. Right? And we've learned a lot about the electrons and learned that it's really difficult to place where electrons are exactly. And we'll talk a little bit about this here. But for now, we just need to understand that we can't know exactly where the electrons are. And so we use this idea of probabilities. We're probably sure as to where the electrons are, but since we can't be exactly sure, things get a little bit fuzzy. And so we call this more of like an electron cloud as to where the electrons are instead of definite orbits. And this model, which we would call today the quantum mechanical model, it wasn't just one person that came up with it, but this idea is what we believe to be really what the structure of an atom looks like. Okay. Now, I want you to realize that the scale of these pictures is not even close. Remember, the nucleus is way, way, way tiny. So drawing it this big is simply there just so you can see it, but it wouldn't even be seen in this picture if an atom were this big. Now, I want to go back to the Bohr model for a minute because even though it's not exactly right, it actually has a lot going for it. First of all, it's easy for us to picture in our heads because we can picture the planets going around the sun. Well, we can picture what Bohr thought the atom looked like. And there is a lot to this that is correct, that is close. And so we're going to start with this model here in talking about the structure of where the electrons are. So the electrons exist in these orbits, although we'll learn they're not exactly like this. And we're going to call each of these orbits, each of these rings, we're going to call them energy levels. And the reason we're going to do that is because the energy levels where the electrons exist are specific places or specific energies that the electrons can have. So these little yellow dots that you see here are the electrons in this atom. And as they get closer and closer to the nucleus, remember the nucleus is positive and the electrons are negative. So there's an attraction there. So the electrons want to be close to the nucleus, right? So the electrons are negative. They want to be close to the nucleus. So the lowest energy place to be, if you're an electron, is right near the nucleus. So this is what we call the first energy level right here. Now you can see the first energy level is not really big. It doesn't have a lot of room. Therefore, as soon as it gets filled up, the next set of electrons would go to the next lowest energy level, which would be the second energy level right here. Again, that's not really big. Eventually it'll get filled up, and eventually there would be a third energy level that the electrons would have to be on, or a fourth, or a fifth, or a sixth, or a seventh. And it turns out that electrons can move from one energy level to another. They can jump from one energy level to another. And to take one electron from one energy level to the next requires a certain amount of energy. The amount of energy is known as a quantum of energy. The word quantum is just Latin for a certain amount. Okay? The certain amount depends, but is always a certain amount. It's always an exact amount of energy. And so we have these quantum of energy that would go into an electron and would cause it to jump up to a higher energy level. If the electron moves down to a lower energy level, it would then release that quantum of energy. So here's a little illustration of that. So energy comes in the form of whatever, but energy comes in and hits the electron. The electron is currently in its lowest energy state. We call that the ground state. But once it gets hit with that energy, it then jumps up to a higher energy level. But being in this excited state, this higher energy level, is not where it wants to be, because that makes it further away from the nucleus. It's attracted to the nucleus. It wants to go back where it was. Once it goes back down to where it was, it has to release that energy. So a quantum of energy comes in, makes it jump to a higher energy level. When it jumps back down to the lower energy level, it releases that quantum of energy. And this is why we eventually will take this Bohr model and convert it into a newer model we call the quantum mechanical version, the quantum mechanical model.